Okay, so let's take a look at another proof. This one's going to be a little bit easier than the last one was. Okay, so if we want to show that, I guess I don't know if you're watching these in order. What I mean by last one is I mean the one where if we assume that it was injective, then f of a minus x is equal to f of a minus f of x. So we are, this is going to be easier than that one. Okay, so we're going to go back to the definitions. So just to recall, so when we looked at the list of showing functions are injective, surjective, or not injective, not surjective, we had some kind of go-to strategies. So recall here that we said that to show a function f is injective, we can prove that if f of x is equal to f of y, then x is equal to y. Don't forget that you always have the contrapositive available at any point. So vice versa, if instead of proving this, you could state that if x does not equal y, then f of x does not equal f of y. So you could prove that statement, prove the contrapositive of this if you would like. So let's take a look now at the statement that we can try to prove. That now if we say g is going to map a to b, f is maps b to c, these are both functions, we're assuming that both of these are injective, show that the composition of these functions is also injective. Okay, so if we think about what our proof is going to look like I said, you could use the contrapositive of this statement if you'd like, but I'm just going to go ahead and use this basic statement. So we're trying to show that a function is injective. We're going to assume that this is true. Now, the function that I'm working with is the composition, right? So I need to be able to start with the composition being the case. So I'm going to start with just kind of basic assumptions. We will assume f and g are injective. Let x and y be elements of some set A. So I'm going to start with elements in A because what's going to take place with the composition is G is going to take place first. Okay, so I need to pull something from the domain of G, which is A. Okay, so now we can assume that these are injective, let this be true. Now, furthermore, we're going to assume that this composition, f composed with g of x, is equal to f composed with g of y. So this is my assumption here. For it to be injective, I'm going to assume this is true, and then I'm going to try to conclude why does x equal y. So this is true. This implies, just using what the compositions represent, f of g of x is equal to f of g of y. So we just replace the little composition dot symbol with actual functions inside other functions. Now from here we have some things that we're trying to work through. Is how do we use these assumptions that f and g are both injective? Now there's going to be a right way and a slightly wrong way to do this. Well, actually a very wrong way to do this. So what we do know is we know some things about these being injective. So which one are we going to deal with first? My suggestion is we're going to deal with f first. Okay, so we want to deal with f first. So since f is injective, so we look at this outermost function. Since it is injective, we have this f of something is equal to f of something else. What that means is that those two insides must be equal to each other. Since f is injective, this implies that g of x is equal to g of y. So if f of something is equal to f of something else, these two somethings must be equal, right? The two insides must be identical. Now we use the statement that g is injective. So since g is injective, this implies, this is just the definition now of injective. This implies x is equal to y. So that's great. Well, what were we trying to show, right? We were trying to show that if this composition f and g of x is equal to the composition of f and g equals of y, if this is equal, then that implies x is equal to y. Well, that's exactly what we have just shown. So hence, f composed with g is injective. And that concludes our proof.